Graz, and we are eager here to listen to your lecture. Please, it's your time to talk. Thank you.
Thank you very much. First, I would like to thank the organizers and technical staff of the CIM for providing this amazing opportunity. I think especially for early career researchers like myself, it can be difficult at times to have the funds to travel and present in conferences. And having this remote presentation option certainly overcomes that barrier, plus healthier for the planet too. In this session, I'll be talking about a new musical aptitude test Dr. Daniel Mullenzeven and I've developed called the TPT, which stands for Timbre Perception Test. But I believe that this newly developed tool can be applied in many areas of music psychology and to do interdisciplinary research. So this presentation will be split into 4 sections. First, I'll talk about what timbre is and about the proposed 3 distinctive dimensions of the timbre space. Then I'll move on to introduce 2 currently existing tools to measure timbre perception and some of the limitations they may have. Next, I'll introduce how we took a novel approach to design an interactive test using reproduction paradigm and demonstrate the interface. In the results, I'll talk about the robustness of the newly developed tool by considering its reliability, factor models, and its correlations with related measures. Lastly, I'll briefly discuss our next step of this project and provide links to all the presented materials here, including the freely available software itself. So to begin with, alongside pitch, rhythm, and loudness, timbre is a primary perceptual attribute of complex sound. However, unlike pitch, tempo, and loudness that are mainly related to a single physical parameter like frequency and duration and decibels, timbre is a multidimensional attribute that arises from complex acoustic properties. It is broadly defined as color or texture of an instrument. And while emerging body of work on timbre have boomed in recent years, for example, we see a lot more talks presented at ICMPC than any other years, still timbre remains a relatively poorly understood auditory attribute. This is presumably due to its multidimensional and complicated nature being a challenge in psychological timbre research. So timbre having this multidimensional attribute, a lot of effort has been put to categorize and identify the dimensions of the timbre space. Certainly not all studies have yielded the same number of timbre space dimensions, but these days most researchers tend to agree that attack time and spectral centroid are the most salient properties, whereas spectral flux, or sometimes known as spectral deviation, are seen as somewhat more controversial attributes. So in our study, we used the dimensions proposed by McAdams and colleagues as basis for our testing dimensions. Later I'll explain this a little further. So to describe these 3 important dimensions, first, attack time is defined as the duration a sound takes to reach its peak volume. For instance, bowing the string of a violin will produce a long attack, whereas playing a note on a piano will produce a short attack. Second, the spectral centroid is defined as the relative weight concentration on the frequency spectrum. Perceptually, it is characterized as the brightness of a sound, generally ruling that a sound is perceptually brighter if the spectral centroid is positioned higher on the frequency spectrum. So here, for example, the trumpet would sound brighter than clarinet, for instance. For the third dimension, while the definition of the spectral flux isn't very clear at the moment, it has been suggested as features to capture the developmental aspects of sound. Perceptually, one way a variation of spectral flux can be distinctively heard is when manipulating the harmonic integer values of the overtones to the fundamental tone. This results in irregularities of phase between harmonic components, which increase the number of beating frequencies that results as dissonant sound. So while there are some concrete dimensions of timbre, there are only two existing tests that sought to measure an individual's timbre perceptual ability, one of which is the timbre subtest from the Proms test battery. So in this test, listeners compare different orchestral instrumental combinations from similar or distant instrumental families. For example, they would hear a sound composed of 4 violins and then asked to compare this with another sound of 3 violins and a viola. And then they would rate how similar the two sounds are on a 5-point scale. So although this testing paradigm provides an ecologically valid approach by employing real orchestral instrument sounds, the acoustical properties of these instrument combinations cannot be empirically measured. And besides, the test may be potentially biased towards classically trained musicians, especially among musicians who have acquired years of training with instruments presented in the stimulus set. And if we think about the commercial music of today, a lot of production include non-acoustical instruments with multiple layers of sound processing technology involved. So for instance, audiophiles, DJs, sound engineers, they undergo years of training so that they can detect the finest details within sounds. So these modern experts may not have an ear tuned for combinations of string instruments, but they may have an extraordinary ability to hear the fine attributes of sound that most normal listeners would miss. So in order to assess wider audience with varying backgrounds of music, listening or playing, exclusively using orchestral instruments is a serious limitation when we consider how preference and familiarity regarding Western orchestral music can differ between individual listeners. The other auditory battery that includes tests related to timbre perception is the psychoacoustics toolbox that runs on MATLAB environment. This toolbox is a comprehensive battery for testing auditory thresholds and implements different kind of adaptive testing methods, including the maximum likelihood procedure, the MLP, and staircase methods. It contains several tests for assessing thresholds, which may have some relations to timbre perception, but they're not exactly designed for the purpose of assessing timbre perception in any direct or comprehensive way. So from the toolbox, the most relevant ones are these 3. So the listener's task for this is to judge among the heard 3 tones, which one is highest in pitch for this, longest in duration, or the one that sounds odd. Again, these measures do not provide a direct link to timbral dimensions, so it has its own limitations. So given these limitations of the existing tools, our aim was to develop a new auditory test that is specific for testing perceptual dimensions of timbre with following goals. First, we wanted to implement a fast, intuitive, and engaging method. Second, we sought to empirically measure differences in perceptual abilities among individuals, not only by the broad definition of timbre, but also separated as distinctive dimensions of perceptual timbre space we looked earlier. Lastly, we wanted to provide a robust instrument that avoids classical training biases. So we believe that developing such tool will greatly enhance future timbre research and enable the investigation of series of novel research questions, such as are there dimensions of timbre in which trained musicians and non-musicians differ substantially? Do certain groups have a biased perception when recalling timbral features from memory? Or is there such thing as absolute timbre perception? So given these aims, we programmed the new test in the max MSP environment. The stimuli were designed using 8 sine waves to generate the complex tone. And we adopted a reproduction paradigm using a slider GUI. So the participants performed 5 trials of match task and 10 trials of memory tasks, of which memory condition restricted their number of playbacks of the stimulus, whereas for the match task, it was unlimited. And the comparison between match and memory was to compare how much the auditory thresholds will vary when fine-tuning to reproduce the tone against recalling the heard tone from memory. Soon I'll demonstrate the interface itself, but let's just have a quick overview on the layout. It's testing the thresholds of the 3 proposed dimensions by McAdams, the envelope, which has this same name for attack time, block spectral flux, and spectral centroid. So in the envelope block, moving the slider would alter the duration of the attack time. In the spectral flux, moving the slider would alter the phase alignment of the 8 harmonics. So moving it to maximally to the right would introduce more number of beating frequencies that results as a dissonant sound, whereas moving it fully to the left would make the sound more consonant. And for the spectral centroid block, we applied a band path filter to locate which frequency bands are bypassed and which frequency are cut. Let me quickly demonstrate the interface. So this is what it looks like when you open it up. Let's start the test. So as soon as you start the test, you would hear the sound coming from the blue sound, and it's indicated by the blue light here. So it's telling me to press the blue sound again. And now we want to compare this with the yellow sound. And then we're going to move the slider bar to adjust the yellow sound. And we're comparing this to the blue sound. And then when you're satisfied of your outcome to match the yellow sound to the blue, then you would move on to the next block. So, okay, so this was the envelope block, and now let's try to move on to the. So in the memory block, you're actually only allowed to hear the blue sound once. So after hearing it once, it's jammed. So when you're trying to press it, it would no longer play the blue sound. So you have to adjust the yellow sound just from the memory from what you heard in the first instance. Okay, and let's just quickly demonstrate. Yeah, sorry about this. Okay, so in the second block, it's the spectral flux. So the stimulus sounds like this. And moving it completely to the left sounds more consonant. Completely to the right would sound more dissonant. Okay.
You have 5 minutes left, okay?
Okay. So to test the validity of the TPT, we recruited quite a large sample of participants to test the TPT for validation. First, we screened participants who may have hearing loss. Thankfully, there were none. Then participants performed the TPT. And there's 3 tests from the psychoacoustics that I mentioned earlier, and the PROM's Timbre subtest in a subsequent order. Lastly, they completed the Gold MSI self-report, which is a short questionnaire that addresses several aspects of musical expertise and engagement. After collecting participants' performance data from the TPT, we examined the correlation metrics and found that all of the match conditions are substantially correlated with each other, whereas the memory conditions show more heterogeneous results. So when observing the factor loadings of these 6 subtasks variables and a single factor solution, it became more evident that the match tasks, shown as the blue circles here, are more strongly attached than the memory conditions in green. So when examining the reliability of the instrument, we could see that it has acceptable to good internal consistency in conventional terms. We also examined the 2 different conditions separately and observed that is more true so for the match conditions than the memory condition. And considering together the weak loadings and poor internal consistency of the memory condition, we actually decided to only recommend using the match condition when examining an individual's general ability for timbre perception. So we recruited fresh new participants to examine the test reliability only for the match conditions, which reported around 0.8 correlation. For the correlations with related measures, we predicted that the performance on the TPT will positively correlate with timbre subtests from proms. We also predicted that individual subtasks would correlate with pairing auditory tests from the psychoacoustics toolbox. However, we did not expect these correlations to be very strong, given that these tests are measuring somewhat quite different auditory attributes. Lastly, we predicted strong correlations with the composite scores of the GOLD MSI index, particularly stronger correlations with perceptual abilities and musical training subscales. As predicted, the TPT was positively correlated with PROMS test, supporting the validity. At the same time, this moderate but not substantial amount of correlation also suggests that TPT is measuring aspect of timbre perception that the PROMS is not capturing. Interestingly, only the spectral flux dimension of the TPT correlated with the relevant auditory tests in psychoacoustics. But as I said earlier, this is likely due to the 2 tests having quite a different approach and measure. Surprisingly, the TPT correlated quite substantially with GOLD MSI and all of its subscales. After excluding this yellow bar named general sophistication, that is composite scores of the REST-5 subscales, musical training and perceptual abilities were most highly correlated, which makes intuitive sense. The others were less correlated. When we compare match condition and memory, we could see considerable loss in accuracy across 3 dimensions, regardless of musical training. More musically trained individuals performed better than non-musicians when fine-tuning the production, but not when recalling from memory. Among the psychoacoustics, PROMS, and TPT, the TPT showed the strongest correlations with GOLD MSI. Performance accuracy increased when participants chose to listen to more repetition. Production test paradigm led to a greater test efficiency, with the total test only taking about 10 minutes to measure 3 different auditory thresholds. So for the future works, we would like to implement this test online to test larger number of participants. We also like to test the divergent validity by comparing this test to other auditory tests. We like to also test the generalizability by comparing real versus synthesized sounds, since the method of testing was quite restricted to a specific situation in this case. We'd use the same acoustical parameters for both the real and synthesized stimuli to examine if we can replicate the same outcome. Okay, so final thoughts. The link for the program is here, and it runs both on Mac OS and Windows, and is freely available. And if you have any questions, you can always contact me. So thank you for your attention. Thank you.